Oh, this is lecture 2 of my Calculus 1 course. We are in part 1 of the course, Function Review. Last time in lecture 1, I gave you an overview of all of Calculus 1. And today we're specializing on a review of function fundamentals. Now, everything that we talk about in today's lecture, you've studied before. This is just a review. But I'm highlighting the things about functions that I think are most important for calculus. You'll recall that a function is a mathematical device that models how one quantity depends upon another. We might denote a function as y equals f of x. The x, as you know, is called the independent variable. You think of that as the input of the function. And then f, the function f does something to f and gives you the output, y. So y is called the dependent variable. Y depends upon what x is. And here the name of this function is f, but we could also use letters like g, h, sometimes Greek letters phi. We also have names of special functions, sine, cosine, log, etc., that we'll talk about a little bit later in part 1 of the course. There are lots of ways to describe functions. Functions can be described with, first of all, formulas. F of x might be the function 3x squared minus 1. So you plug in x, and the output is 3x squared minus 1. Another way to describe functions is with graphs. So here is the graph of a function g of x, and you can see from the graph that g of 1 is equal to 2, because if you plug in 1, you get a y value of 2. Also, g of 2 is 2.5. Plug in 2. You're at 2.5. And it looks like g of 3 is equal to 2. So you can compute function values by looking at the graph of a function. You can also describe a function with words, like maybe wx is the function where wx is your weight at the age x. And we'll find that in this course we tend to use these 3 different ways of describing functions. We're especially going to be concerned with the interplay between describing a function with its formula and with its graph. But often words will come into play too. And occasionally we'll describe a function with tables. Like here's a table that roughly describes a function h of x. When x is 1, h of 1 is 3. h of 1.5 is 1. h of 2 is 1, and so on. So as we go on, we'll see these different types of describing functions in play. I'd like to spend some time talking about the notions of the domain and range of a function. The domain of a function f is the set of all possible input values for f, whereas the range of f is the set of all possible output values for f. So to illustrate that, think about the function that's described here by its graph, y equals f of x, just this little segment of a curved line between x equals a and x equals b. In this graph, you could plug in a to f, and you get the point a f of a, right there, at height f of a. No, you couldn't go to the left of a. You can't plug those values into f. They're not valid input values because there's no part of the graph there. But you could increase x past a, and you get the corresponding point xf of x up there on the graph, and a corresponding y value for each x. So if you look at what y values are swept out there, for x going between a and b, f of x goes between here and there. So the allowable values for x in this function, the set of all possible input values, would be the values of x in this closed interval between a and b. And that's the domain of f. Whereas the range, it's all of these y values between this number c and this one d. That's the set of all possible output values for f. So the interval from c to d is the range of f. So here we'd say the domain of f is the closed interval from a to b, and the range of f is the closed interval from c to d. That's the set of all output values. Now, let me quickly remind you of interval notation. We're going to use it a lot in this course. You've seen it before. Remember that the closed interval from a to b is denoted this way, with an a and a b enclosed in square brackets, and that literally stands for all the real numbers x, for which x is between a and b, and possibly equal to a or b, this closed interval right here. Whereas we could also have an open interval from a to b. It's denoted by a and b in parentheses, and it stands for all values of x, where x is between a and b, but not including those values of a and b. It's not permitted to be equal to a or equal to b. That's the open interval. And it's an unfortunate notational accident that the open interval from a to b, this little notational package, also stands for point on the xy coordinate system, but that it's usually clear from context what we're talking about. And you can have half-open intervals. Like this half-open interval is open on the b side but closed on the a side. It stands for all x, all real numbers x, for which x is greater than or equal to a but less than b. And it's quite possible that in intervals, one end of an open interval might be infinity or maybe negative infinity. The interval from a to infinity would be all real numbers x, such that x is greater than a. You might have an infinite interval that's closed at a too. So if this looks a little hazy, go back and review this. It's stuff we've seen before, but we have to move on. I'd like to continue talking about domain and range. It's really the domain that's more important. Range, sometimes you don't have to worry too much about, but so often in calculus you'll be dealing with a function and your most immediate question is, what can I plug into the function? And that's going to be your domain. Let's take an example, f of x equals x squared minus 1. The domain of this function is the interval from negative infinity to infinity, which is all real numbers. You can plug in any real number for the input there. And what about the range? Well, if you think about that, it's x squared minus 1, and x could be 0, which would give you negative 1. And then if x is positive, its square is going to be positive, so you're adding to minus 1. So the range is going to be the interval from minus 1 to infinity. Here's another example. Let's let f of x be the area of this shaded region. And what we have here is a 1 by 1 square inside of a larger square that's an x by x square. So the shaded region here, you could figure out as, let's see, the big square is x by x square units. So that's x squared square units, but then you have to subtract off the area of this inner 1 by 1 square. So the area of the shaded region is x squared minus 1. Now notice that's exactly the same function that we had up here. But look at the domain of this function in our second example. In this picture, x has to be bigger than 1 to enclose some shaded area. And it could be arbitrarily large. So the domain is the interval from 1 to infinity. Whereas the range could be anywhere from 0 to infinity. The smaller and smaller x is, the closer and closer to 1, the smaller this shaded area is. So the shaded area is very close to 0. But as x gets bigger and bigger and bigger, the shaded area would get bigger and bigger as well. So the range would be the interval from 0 to infinity. So notice that in this example, the formula for the function is exactly the same, but the domain and range in these two examples differ. And that's an important distinction. A lot of times in this course, when you have a function f of x that's described in words, it'll also have a formula expression, but the domain and range would have a special interpretation based on the intended meaning of that function. And we'll see more of this as we go along in this class. But for now, there's a convention that if it is not stated or implied otherwise, the domain of a function is assumed to be the set of all numbers for which the function is defined. So, for instance, if f of x is 1 over the square root of x, what is the domain of that function? Well, it's the set of all values of x that you could meaningfully plug into f. And let's see, the x is inside a square root, so it has to be positive. Okay to have a 0 in the square root. However, in this case, you'd be dividing by 0 if x were 0. So x has to be positive. So the domain is the interval from 0 to infinity for this particular function. Here's another example. Let's find the domain of the function f of x equals 1 over the square root of 4x squared plus 4x minus 3. Now I'm going to simplify this by factoring that expression inside the radical. We get 1 over the square root of 2x plus 3 times 2x minus 1. And in looking at this, for f of x to be defined, this expression down here inside the radical, it has to be positive. It couldn't be negative because we can't take the square root of a negative number. In calculus, we deal only with real numbers. Nor could this expression be 0 because then we'd be dividing by 0. So 2x plus 3 times 2x minus 1 has to be positive in order for f to be defined. It cannot be 0 or negative. Those are not allowable values. So in finding the domain, we could look for the values where this function is 0 or negative and exclude those. It's easy to tell what values of x make this product equal to 0. 2x plus 3 times 2x minus 1 is equal to 0 if x equals negative 3 halves or x equals 1 half. You can see that from the factored form here. So those two values of x are definitely not in the domain of our function f. They're not allowable values. But we also have to think about what value of x might make this product negative. We want to avoid those. We only want the product to be positive. And there's a standard way of doing this. You can take the x-axis and first of all plot these two values of x that make this product equal to 0. There they are, negative 3 halves and positive 1 half. And then we're going to look at these factors individually, the 2x plus 3 and the 2x minus 1. Let's start off with the 2x plus 3. It's equal to 0 right here at minus 3 halves. And if x is on the right side of minus 3 halves, you can reason out that 2x plus 3 is going to be positive. So we're going to put positives here to indicate that we're positive for those values of x. Whereas if x is less than negative 3/2, like x equals -2, 2 times -2 plus 3 is negative. So we'll put negatives there to indicate that for these values of x, to the left of -3/2, 2x plus 3 is negative. We do the same thing for the other factor, 2x minus 1. It's equal to 0 when x is equal to 1/2, but if x is to the right of 1/2, like if x is equal to 1, 2 times 1 minus 1 is going to be positive. So we're going to put positives here to indicate that for all of these values of x to the right of 1/2, 2x minus 1 is positive. And then on the other side of 1/2, for any of these values of x, 2x minus 1 is negative. So now look at the product of 2x plus 3 times 2x minus 1, this thing that we're interested in, that we don't want to be negative. On the interval from 1/2 to infinity, it's a positive times a positive. So we put positives here to indicate that for these values of x, 2x plus 3 times 2x minus 1 is positive. Whereas for this middle interval, where x is between -3/2 and 1/2, this product is a positive times a negative, and that's a negative. But then on the interval from negative infinity to negative 3/2, it's negative times negative, and that's positive. So we now see, splayed out on this coordinate system, that 2x plus 3 times 2x minus 1 is positive as long as x is greater than 1/2 or less than -3/2. So I'm soliding in all of those values of x, for which 2x plus 3 times 2x minus 1 is positive. So this part of the number line together with that part of the number line. So that shaded end part, that's the domain of our function f. So answer, the domain is the interval from negative infinity to -3/2, this part, union the interval from 1/2 to infinity, this other part. The domain is 2 intervals. The stuff in the middle here, that's not in the domain of the function because it would give you a negative inside the radical. Nor can you have x equal to -3/2 or 1/2 because in that case, what we have inside the radical would be 0 and we're dividing by 0. So here's our domain. So you should get some practice finding domains of functions and work some exercises in the book. Let me talk for a moment about the graph of a function. You'll remember that the graph of a function f is the set of all points x f of x on the plane for which x is in the domain of f. So take a point x in the domain of a function, look at the point x comma f of x on the plane, and that's a point on the graph. And you do that for all possible values of x in the domain, and you get the graph of a function. And usually it's some sort of curved line. And note that this is the graph of the equation y equals f of x. It's the set of all, for any value x, the y coordinate is f of x. Y equals f of x. So here's an example of a typical graph of a typical function. Take the function f of x equals 1 over 4x squared plus 4x minus 3 from the previous slide. And here I've used a graphing utility to graph it. And you'll notice that as on the previous slide, the domain is the interval from 1/2 to infinity, union the interval from negative infinity to -3/2. There's this little part in the middle here that doesn't correspond to any point on the graph. There are lots of ways to combine functions. You know, you can add them, subtract them, multiply them, and so on. And you've studied that in your pre-calculus course. You also studied composition, and I want to say a few words about composition because it plays a really key role in calculus. Given two functions f and g, we can form the following new functions. There's what's called f composed with g, and also g composed with f. And f composed with g, that's the name of a function. It's defined this way. If you plug in an x, you get f of g of x. F composed with g of x is f with g of x plugged into it. And g composed with f, that's the name of a function, and it's defined this way. When you plug in an x, g composed with f of x is g with f of x plugged into it. So let's look at some refresher examples. Take the function f of x equals x plus 1 over x minus 1. G of x is x squared plus 1, and h of x is x minus 1. Let's look at f of g of x. So that would be the composition f composed with g of x. Now, to figure this out, it's helpful to think about our function f that we're plugging the g of x into as being a sort of template. Maybe get rid of that x and just think about that as f of a blue box is the blue box plus 1 over the blue box minus 1. And you could plug in anything into this blue box. In particular, you could plug in a g of x into the blue box. So f of g of x would be a g of x plus 1 divided by g of x minus 1, which we have here. Then in turn, g of x is x squared plus 1. So we replace each of these occurrences of g of x with that. And then we simplify. So f composed with g of x is x squared plus 1, x squared plus 2 over x squared. I want to point out that although we have this circle representing composition, f composed with g, really on a daily basis we tend to write our composition as just f of g of x rather than f composed with g of x. That's pretty standard. Let's also work out g composed with f. We'll do it in opposite order. So for g composed with f, g is the function that whatever you plug into it, you square it and add 1. So here we are plugging in f of x to g, so we would square that f of x and add 1, and our f of x is x plus 1 over x minus 1. So that gets squared, and we add 1. So there's our function g of f of x. Notice here that f of g of x and g of f of x, they're different functions. And that's standard. You should expect to get different functions. This is not like multiplication where order doesn't matter. It's composition. It's very different from multiplying functions. In composition, you're plugging one function into the other. As our third example, look at f of h of g of x. Here we're taking a three-tiered composition. We do h of g of x and we plug it into f. So that would be, let's see, f of any quantity is the quantity plus 1 divided by the quantity minus 1. So if we plug in h of g of x into f, we get that quantity h of g of x plus 1 divided by h of g of x minus 1. Now, h of x is x minus 1. Whatever gets plugged into h of x, you just subtract 1 from it. So h of g of x would be g of x minus 1. And that happens here and also there. And finally, you simplify, and you get x squared plus 1 over x squared minus 1. Now, in these examples, we've taken three functions and we've composed them kind of building up more complex functions. Actually, the reverse process is what is going to be the most important in calculus. For example, think about the function h of x equals the square root of x squared plus 4x minus 3. In calculus, you often want to break down a complicated function into the composition of other functions. So let's see if we could write this h of x as the composition of two functions. One solution might be the following. Let f of x be the square root of x. So f is the rule that says whatever gets plugged into it, you take its square root. And then let g of x be the polynomial 4x squared plus 4x minus 3. So if we do that, our function h of x here is f composed with g of x. In calculus, it's very important to be able to recognize that a function is a composition of other functions. And typically when you want to exploit that composition of other functions, you're looking for a way to break up your function into simple elemental pieces. I have students who will correctly solve the same example, perhaps like this. Write this same h of x as a composition of two functions. Sometimes students will say, well, I'm going to let f of x be square root of x minus 3. So whatever you plug into that, you subtract 3, and then you take its square root. And then I'm going to let g of x be the function 4x squared plus 4x. And sure enough, h of x is f of g of x. And I'll always give them full credit for that because it's a correct answer. However, it really is not in the spirit of what we're going to be looking for in calculus. And calculus, where this composition really comes into play, you're going to be looking into ways of decomposing your functions into compositions of simple elemental functions like square root and a polynomial. And this is a little more complicated here. So a correct answer, but it's not quite what we're looking for. Now, if this sounds a little bit vague, it's the kind of thing that when you start using it later in the course, it becomes second nature and you don't think about it twice. We'll get there. So here's another example. Here's a function big F of x. Write it as a composition of functions. Well, you'll notice that it's a fraction, and on the denominator is this h of x that we had up here. So taking our cue from the example up at the top, as a solution, you might want to say, let's let little h of x be 1 over x because we got a reciprocal going on here. F of x is the square root of x, and g of x is the polynomial 4x squared plus 4x minus 3. And I think you can convince yourself that big F of x is h composed with f composed with g of x. It's h of f of x. It's h of f of g of x. F of g of x would be this expression, and then we're reciprocating that by taking h of it. H is whatever gets plugged in, you take its reciprocal. So often you'll be looking to decompose a function as not just the composition of two functions, but sometimes 3 or even more. Let's move on. I want to talk about the idea of shifting functions. You've seen this in pre-calculus, and it's actually really useful in calculus. And well, it's not like a really important idea in calculus, but it happens enough that I want to talk about it. Imagine you have a function f of x, and so for any x, this y value above it, going from the x-axis to the graph, that's f of x. And imagine you took f of x and you got a new function by adding a constant c to it. You'd just be adding a c to each f of x. So that has the effect of moving the graph of y equals f of x up c units. So let's let c be greater than or equal to 0, as it is in this picture. The conclusion is that the graph of f of x plus c is the graph of y equals f of x moved up c units. And of course, if c were negative, we'd be subtracting, we'd be moving down c units. The graph of y equals f of x minus c is the graph of f of x moved down c units. And that shifts graphs vertically. You can also shift graphs horizontally. If we take the graph of y equals f of x, I want you to think about what happens when you have the graph of f of x minus c. And here the x minus c is inside of f. To figure out what that graph looks like, take a typical value of x. And into f, you're plugging in x minus c. So you go back c units here, x minus c. And then you take f of that. F of x minus c is this y coordinate. But you're graphing y equals that for this particular x. So you're really over here. And that would be a point on the graph of y equals f of x minus c. So the graph of f of x minus c lies c units to the right of y equals f of x. So in summary, let c be greater than 0. The graph of y equals f of x minus c is the graph of f of x moved c units to the right. And also, as you've seen before, the graph of y equals f of x plus c is the graph of y equals f of x moved c units left. Here's another shifting operation. If you think about the graph of y equals f of x, if you suddenly change that to y equals minus x to get a new function by multiplying the first function by -1, that would just negate all of your y values. It would reflect that function across the x-axis. There are some other shifting operations that I'm not going to talk about here, but read your text, refresh your memory. We'll conclude with an example. Typically, it works like this. In calculus, you're always working with functions, and maybe you've got a function like f of x equals 2 minus the square root of x plus 3, and that's just given to you. And you need to work with it. You need to understand what it's all about. Shifting operations allow you to understand that function in terms of simpler functions that you already know. So imagine you wanted to sketch the graph of 2 minus the square root of x plus 3. You could approach it like this. First of all, this f of x, it's got a radical inside it, so it's a lot like the graph of y equals the square root of x, of which you're familiar with, which looks like this. So you sketch that in. Now, what's next is you have the negative of the radical here in our f. So let's take the negative of the square root of x, and you're reflecting that square root of x across the x-axis. But then we have inside the radical an x plus 3 and not an x. And we know that changing this x to an x plus 3 using the shifting operation on the previous slide is going to be this graph of the square root of x moved 3 units to the right. So we get this curve as y equals negative square root of x plus 3. Now finally, to get our function f, we need that plus a 2, and that's going to move this whole thing up 2 units. So here finally is our graph of y equals 2 minus the square root of x plus 3. You can erase all the other stuff, and you have a quick mental impression of what this function looks like. You'll find yourself doing this a lot in calculus. Some of these are, they may be complicated enough when you're working examples in the textbook in pre-calculus, where there's almost a point of diminishing returns. They get so complicated that it just better to graph the function with the graphing utility. But so often it'll happen that you'll have a simple function like this one, or maybe one even a little simpler than that. And just with a few shifting operations, you can very quickly, in the mind's eye, see what that function is all about. So that's it for today. That was just a very quick function review. It should be familiar to you. If anything looks hazy, read about it in your text, refresh your memory. Here's what we're going to do from here on out. Next time, Lecture 3A, where we'll talk about trigonometric functions. We'll review them. We'll spread that over 2 lectures. Lecture 4 is going to be inverse functions. Then 5A will be exponential functions, logarithm functions. Then we'll talk about what's called the natural exponential and log functions. And then we'll spend 2 lectures, lectures 6A and B, on inverse trig functions. Now, after that, we'll be done with part 1 of the course, which is the function review, and then we can start doing some calculus. So we've got a good bit to do before we do the calculus. So next time, lecture 3A, trigonometric functions. I'll see you there. Goodbye.